Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome back once again to this lecture series on aluminium based alloys and metal matrix composites. So we have been discussing about this different mechanisms of grain refinement during the melt inoculation process. Okay. So far we have discussed about 4 different mechanisms through which the heterogeneous nucleation occurs in the melt, and these are as follows: carbide boride theory, peritectic theory, peritectic hulk theory, and then we also discussed about the hypernucleation theory. Okay, so these are the 4 different mechanisms that we have talked about in detail in past couple of classes. Today we are going to see one more mechanism, and that will be the solute theory. This theory suggests that both nucleants and segregating solutes influence the grain refinement. And the effectiveness of titanium has been already recognized for its grain refinement ability due to the fact that it has a high segregating tendency, right? And this extent of segregation is given by a parameter known as growth restricting factor. I'll come back to this and explain what it is. So if you see the number of grains per unit volume, which basically is related to the grain size also, that would depend on the number of particles per unit volume. Okay. So let's say the number of grains per unit volume is this one, NVG, and the number of particles per unit volume let's say that is written as NVP. So the number of grains will increase with increasing number of particles, but that will occur up to a certain value of the number of particles. So this will increase up to a critical value, and beyond that it will saturate. So if I show it as a plot between these two parameters, so it will increase to a critical value. As I said, the number of grains will increase with number of particles up to a critical value, and then beyond that it will saturate. So what it means is, beyond saturation, all particles do not act as nucleation sites. So for a fine grain structure, the growth has to be restricted during the solidification process. So that is what is actually given by that growth restriction factor which I mentioned before. And the growth rate is actually inversely proportional to that parameter called growth restricting factor, or GRF. Okay. So higher the GRF, lower will be the growth rate and finer will be the grain size. And if you want to define GRF now, it is given as follows. Where m is the slope of the liquidus, C naught is the concentration of solute in the melt, K is known as the equilibrium partitioning coefficient, and it is given as the ratio of CS and Cl, wherein CS is the concentration of solute in the solid. So this is basically the solid composition. Similarly, Cl is the concentration of the solute in the liquid or liquid composition at the interface. So as I said before, titanium has a higher tendency for segregation and it leads to a high GRF also. And therefore it has been found as a very effective grain refiner that we have already discussed before, right? So high GRF is one of the main reasons as to why titanium is so effective in grain refinement. So if you look at the values of GRF at the peritectic composition, for titanium it is 31. Whereas for other elements such as zirconium and chromium, it is much lower. For zirconium, it is 5, and for chromium, it is only 0.5. And at some other compositions, particularly the concentration in which titanium is generally added for grain refinement, that is in this range, 0.01% titanium, the GRF for titanium is around 2.1. Whereas for a boron concentration of this 0.001%, GRF is 0.02. Right, so you can see again titanium always gives rise to a high GRF and therefore it is a very effective grain refiner. While talking about grain refinement by melt inoculation, one thing that you should always remember is the fading and poisoning. So this is another very important aspect of this entire process. How effective would be the grain refiner or how good will be the grain refinement efficiency, that would depend on how effectively this fading and poisoning has been controlled during the grain refinement process by melt inoculation. Okay, so as the name itself suggests, fading means the grain refinement efficiency will decrease or will be lost. Okay, and there will be certain phenomena which can lead to that decrease in the refinement efficiency. Okay, so that's the poisoning effect, which can lead to a decrease in the grain refinement efficiency. Okay, so let us talk about these two in little more detail as to what happens during this process and what can be done to avoid it so that you can get a fine-grained microstructure. So let's talk about fading first. This essentially means the nucleating surface that you had is either lost or poisoned, and it has lost its grain refinement ability. So we have seen that the solubility of titanium in aluminium can go up to 0.25%. Solubility of titanium in liquid aluminium is 0.25%, right? Whereas it is added in a very minor quantity, which is only 0.01%, right? And therefore, the Al3Ti particles that you have in the melt are not stable when you have titanium in such a low concentration, okay? Because titanium can dissolve, since the solubility of titanium in liquid aluminium is much higher compared to the concentration in which it is added, okay? So this will lead to dissolution of these particles with time. So Al3Ti particles will dissolve with time. And as a result, if you hold the melt at that particular temperature at which the grain refinement is done, then the grain refinement efficiency of Al3Ti would be lost, because this is going to dissolve if you continue to hold the melt for a long period of time, okay? So the dissolution rate will depend on the holding time. Right, so if you have lost these particles due to this dissolution process, then your grain refinement ability is also lost, okay? When the particles themselves are not there, how can you expect them to act as grain refiners? So this is one theory of fading, which says that the particles would ultimately dissolve because the solubility of titanium in liquid aluminium is much higher compared to the concentration in which titanium is actually added, okay? And there is one more theory for this fading process, and that is the particle settling theory. So for these particles to act as the heterogeneous nucleation sites, they have to be kept suspended in the liquid metal. And therefore, if they settle down, their grain refinement efficiency will come down, okay? So that is what this theory suggests, that the particle can settle down as you keep on holding the melt, okay? And as a result of that, the grain refinement ability or the efficiency will come down. Okay, so this can happen if you continue to hold the melt for long. But the grain refinement can be recovered by stirring the melt. Because if you stir the melt, these particles will be again suspended and they will act as the heterogeneous sites. Okay. This can be also depicted graphically. On the x-axis, you have the holding time in log scale, and on y-axis, you have the grain size. Right, so as the grain refinement occurs, the grain size will decrease. But if you continue to hold for long, the fading will take place and the grain size will again increase. So here Tc is the contact time. That is the time elapsed between addition of the master alloy and casting. And this is the grain size, which is known as the ultimate grain size, or UGS, the grain size corresponding to the contact time is known as the ultimate grain size. Okay, so that is the minimum that you can achieve. That is the minimum grain size that can be achieved. And if you continue to hold the melt beyond this time, then due to the fading effect, the grain size will again increase, as you can see. And now, after a prolonged holding, when the particles would have settled, if you start the melt, then you can see a recovery. That means the grain size will again decrease as the grain refinement recovers. Stirring of the melt will again get these particles suspended into the melt, and they will again act as the heterogeneous sites. So that is why when you stir it, you have some recovery in the grain refinement. Okay. Now there is one more aspect, that is the poisoning. So the poisoning is with regard to some adverse effect of certain elements on the grain refinement. So elements like chromium, zirconium, lithium, and high levels of silicon will adversely affect the grain refinement. And this will lead to coarser grains. If such elements are present and they have this poisoning effect, then the microstructure which will be obtained will be coarser. Compared to a microstructure which will be obtained without the presence of these elements. And the poisoning effect occurs, it comes due to some interaction between these kind of elements and the grain refining constituents that you have in the melt. And there are certain mechanisms proposed to explain these interactions. For example, if we talk about zirconium, a ZfB2 coating, zirconium can form zirconium boride and it can coat over the TiB2 particles. So due to the presence of this ZrB2 layer, which is not a very good grain refiner on TiB2 particles, the grain refinement ability of TiB2 will be lost. Okay, or it can also occur by some other mechanism. For example, substitution of titanium by zirconium. So here instead of TiB2, you will have both titanium and zirconium because some amount of titanium will be replaced by zirconium. Okay, and as I said, zirconium boride is not really a good grain refiner. So when zirconium is substituted in titanium boride, its grain refinement efficiency will decrease. And this also changes the lattice parameter. So the orientation relationship and all that which titanium boride would have had with aluminium will also change. And because of that, the grain refinement efficiency is also going to alter. Or it can also happen that zirconia may displace titanium from the particle liquid interface. And apart from that, complex compounds such as aluminides, borides, silicides, which do not really have any nucleating ability, can also form. and that can lead to the decrease in the grain refinement efficiency. Okay, so this is how the poisoning occurs due to the presence of certain elements like that, which will poison the actual grain refinement element which is being added to the melt. Okay, so with that we come to the end of this lecture. Thank you for your attention.